I'll just recap the discussion and then we'll going further, right? So we are discussing that integer linear programming formulation of this scheduling problem, and specifically we try to solve the minimize latency under resource constraint. So it means that we have given the upper bound of resource available for each type of resource that is given to us, and our objective is to identify what is the minimum latency needed to schedule the behavior using those resources, right? And so if you remember, so the problem is like this: I have that given sequence graph is given that V, and this so every node has a particular delay. Delay is basically the number of time step needed to execute that particular behavior, and the dependency, which is E, right? And also you have given the upper bound AK of number of resources. So each type of resources, and the resources type is like multiplier, adder, ALU, and so on. And what is the scheduling problem that we have decided? Just that we try to map each such node to a timestamp, right? So I try to assign an integer value to each such node, right? So that scheduling is a function phi, which is basically assign each node to a integer value, such that it satisfies the timing constant or the dependency constant. Sorry. So dependency constant is something. If I schedule a node Tj at node, I mean a j node j at time step Tj, each subsequent node I should be only scheduled when this node is finishes execution, right? And this particular node Vj will finish its execution at t plus Tj plus Dj minus 1, that number of time step, and then next step I can schedule the successor node Vi, right? And also at every time step, the number of resource getting of each type should be less than of the resource available, right? So what does it mean? That every time I can if say there are two multiplier available, I can schedule at most two multiplier at the time step, right? So this is tau t vj is basically nothing but the type of operation of vi, right? Which is so the all the same type of operations whose type is k should and it is actually, if it is live at time step L, that should be less than AK. Okay, that is what I have already discussed in the last class. And I want to find out this value Tn. Tn is the schedule time of the last node of this, that sync node, which is minimum, which will ensure that this is the minimum latency time schedule, right? And what we have seen that, so how the ILP formulation works, what we have done in the last class is that we in the ILP is basically we have to have an objective function minimization of some expression, and we have certain constant, right? So to identify, so what is our objective in this, we have to find out the timestamp or the clock where is a particular operation is getting executed. So what does it mean? We need to find the start time of a variable, right? So what we have done, we have taken a Boolean variable xil. So if xil is equal to 1 or true, if that operation vi is scheduled time L, right? And we have n number of operations, and the timestamp is if we assume that this lambda bar is the maximum number of timestamp needed, because lambda is something we have to is our objective is to minimize this value of lambda. So its timestamp is possible value is 1 to lambda plus 1, because lambda plus is for the sync node. Okay, so we'll assume this binary variable or the Boolean variable is 1 if a particular operation I or vi is scheduled in time step L, otherwise 0. So this is what is the variable, and we want to find out the value of this particular variable, right? That is what we try to obtain, and we have already discussed that. So how many variables are there? It is n into lambda plus 1, right? So there's no any variables are there, but for a particular I, only one of the value will be 1, right? That means the unique start time. So only a particular operation can start in a particular time step, right? It cannot start in multiple time steps, right? So xil, this particular value xil, this xil is il is basically 1 only for one L for a particular I. Right? So that is something obviously, and rest W is 0. So, and how can I identify the start time of a variable? That is given by this expression, which is something you should understand. So xil is 1 if operation vi at starts at time step L. So if I multiply that particular uh, mm, xil with L, so in that particular time step L, where this operation vi is going to start, this will be 1. And if I multiply this with L, so I'll get the value of L or the timestamp where this particular operation will be executed. So for a so as I declared in the last class also, x say 1 1 plus x12 plus x13 plus x14. So suppose there are 4 timestamp, right? So lambda is say 4, and then for operation v1 there are 4 possible values, right? So if I just multiply this with say 1, so 1 into this, 2 into this, 3 into this, and 4 into this, what will happen? Only say if the operation is starting in time step 2, say I'm like talking about, so this will be 1 and rest will be 0, right? So this will summation will be 2. So I'll tell that particular operation 1 is actually starting at timestamp 2, because rest this will be 0 because x11 is 0. So if you multiply something, it will be 0, right? So this will be 0. This is also 0. This is also 0, right? So I tell that this is the start time of this. So this is how we are going to represent the whole thing. So what are the constant? Let us start writing the first. So obviously that a particular operation can only start in a single time step. So whatever the possible xil for a particular variable I, their summation will be 1. So where I am going to vary this L, here the summation is basically from L equal 1 to lambda plus 1. So for all value of L, for a particular value of I, the summation will be 1. So which is ensure that very unique start time, right? So you try to understand this. I'm repeating and taking a little bit time because last class I was actually went through these things a little bit in hurry. So just to make sure that you understand the things clearly, I'm repeating the whole process for say 5-10 minutes. Okay. So the next thing is kind of the data dependency, right? The sequencing relation is nothing by data dependent. So this is basically unique start time, and this is data dependency constant, right? So data dependency constant must be set. So I already explained the data dependency constant is this. Now I can replace this by this, right? Because I already explained in the previous that a particular ti, if I multiply with this xil with L, their summation will be nothing but ti. Right? That is I have already explained in the this slide, right? So this is what I'm just trying to talk about. So this is nothing but the summation rule is basically ti, start time of variable I, right? So I just replace this ti by this, pj by this, and dj is already that. So basically this is my constant one, that all the data dependency constant will be satisfied. How many such constants will be there? I will have for each edge, right? So if the number of edges e, I will have e number of such constant. And how many constants will be there for this? It is for each node, right? So for each v. So there will be, if there are n number of such nodes, so I will have n such constant here, e number of constant here for data dependency. And the third constant is basically the resource bound. This I have already explained in the last class. Let me explain again that. So AK is the resource bound. So that every timestamp I can utilize at most AK number of resource for a type K, right? So K, the number of resource can be of n resource type, right? So how can I identify what are the operation is active at a particular time step L? So that is very easily can be doable. So I can explain again whatever I just in the last class, that. So suppose this is your timestamp L, right? So if a operation starting here obsess, I mean I'm talking about say particular type, say K or say multiplier only. Okay. So if it is starting here, then also it is going to use a particular multiplier in this step, right? So similarly, if that operation drawing with is bit difficult. Anyway, so so if the operation is starting from this clock also in the previous clock L minus 1, then also this operation is active in this step. And if it is starting from L minus 2, then also it is active. And so this way, if you go up and say you are starting from a state L minus 1 plus, sorry, L minus di minus 1, right? So minus 1. So in that step, also if it is starting, then it's going to finish in this step, right? So if it is starting at this state, it will finish at this step. So these are the, so if starting at L minus di minus 1, L minus di plus 1, sorry, because this is d minus ij. So in that step, if something start, then also it will also going to finish in this step. So in all possible case, if operation, if schedule here, or at this step, it is going to be active in this particular time step L. So I have to assign a particular type of resource at that time step, right? So this is what is given by this. That
Yes.
yeah. So it's
Excuse me,
basically
sir.
L
Sir,
minus plus 1 to L. So if any operation, if starting in that particular time step, so that means this operation is going to consume a resource at that time step L. So their summation should be less than AK, and this is for each type of resource, right? So here K is varying from 1 to n resource, right? And L is varying from 1 to lambda plus 1.
excuse me,
So
sir.
yeah, please.
Sir, shouldn't we just consider L varying from 1 to lambda? Why do we need to consider lambda plus 1? There won't be any resource at the sync node.
But yes, because we have taken that graph as that way, so obviously when you solve the problem, that sync node is going to be scheduled in lambda plus 1. So rest of the things will be scheduled in till lambda, right? So that is why you are taking lambda plus 1, just to make sure that we have the, because if you see the dependency graph, let me just go back. Uh, as yeah, so suppose you have this dependency graph like this. So this is my sync node, right? So if till this point my graph take lambda, so I mean the way I have drawn the graph is that this must be in lambda plus 1, right? So that's why I just considered everything for lambda plus 1, but sync is node is which is single cycle operation, and it's always scheduling lambda plus 1. Just to make the formulation uniform, we are taking lambda plus 1. And I'm making sure that lambda plus is basically reserved for sync node. The rest of the times are available for scheduling of the actual operation. Okay. So this particular resource, as I mentioned, that it's basically I'm making sure that a time step L, in a time step L, how for each type of resource, all the operation that is active at time step L, this is actually calculating number all the operation that is active at that particular time stamp. So their summation should be less than of the type of the resource, right? So if you just look into this particular formula a little bit carefully, you'll understand this, right? So this is what is the constant I have identified. And now what is the objective function? So I want to my objective function is to minimize this CT bar T. So T is nothing but by the start time vector, right? So T is basically a vector, right? So basically it is the start times, right? Say T1, T2 to Tn. And you know that T1 is the start time of operation V1. And this is this, right? So this is the start time. That is what we are going to calculate. And I can actually represent this Ti in terms of Xij also. And this Ct is also a vector. C is a constant vector, right? It's a constant vector. And based on your objective function, you basically have many value. And I already argued that if C is basically 0, 0 to 1, it's basically that means you try to minimize the, so if you basically multiply this is what, this is nothing but multiplication of these two vector, right? So that means you are multiplying 0 with t1, so it will become 0, 0 with t2, it will be 0, right? Finally it is just the tn. So if I just consider um, this particular vector of c, so my minimization function will become, yeah, so my minimization function becomes is basically minimization of Tn, right? So just minimization of Tn. If I consider Ct bar, Ct C is basically all zero, only the last element is one. So my minimization function become minimization the value of Tn. So that means I want to get a schedule which actually is take the minimum number of time step, right? And so my ILP formulation for this MLRC problem is like this: minimization of latency under resource constant, that I want to minimize this function Ct bar t. T represent my vector of start times, and C is a constant vector. It can vary for my purpose, and then it satisfy my unique start time, dependency constant, and resource constant. Right. So if I just have this, and if I fix the value of this constant back to 0001, I am going to get a schedule which is basically give me the minimum time, right? So this is what is all about. And then what I explained with an example, that if you have say two ALU and two multiplier, right? So there are two type of resource, multiplier and ALU. ALU is going to perform this all plus, minus, greater than, less than all operations, and multiplier is just the multiplier, right? So my A1 is 2 and A2 is 2, and I assume that all operations are single cycle. That means DI for one, DI is one for all operations, right? So for simplest option. And then what I say, unique start time. Here, if you, I already told you in the last class that this mobility, which basically makes sure that what are the possible time where that particular operation is schedulable. So I can assume that the mobility is, I can vary this, although this particular equation, you see, it is basically from j is 1 to lambda plus 1. But say for operation 1, I know that this particular operation mobility is 1, so that means it must be scheduled at time step 1. There is no other alternative, right? So I can just say ki x11 is 1, so it is already done, and x12 is 0, x13 is 0, x14 is 0, right? And similarly for operation 6, it has mobility 2, so it can schedule in a time step 1 or time step 2. So I'm just making that x1 is 6.1 and 6.2 is 1. So that means my ILP will tell either 6.1 is 1 or 6.2 is 2, or 6.2 is 1. One of them is 1, right? So that is actually making sure that only in one time step C2, this operation 6 will start. So this way, for each node, I will have a set of in constant, and then I have the data dependency constant. So where I'm saying that the possible start time of, say, if I just take this age, this is for each age. So possible start time of of node 6 is this: either it is in time step 1 or time step 2, and the possible start time of operation 7, which is nothing but this 2 into 7 2 is the start time. If it's executed, starts at time step 2, it is 1, x7 will be 1. Similarly, if it starts at this time step 3, then x7 will be 1. So I'm just multiplying that with 3, right? So possible start time of 6 minus possible start time of this should satisfy the dependency, or the execution time of 6, which is 1. So these two times start time should satisfy the execution time of this operation 6. So this is what this equation all about. Similarly, for each age, I'm going to add the constant. I'm going to add the constant for
Sir,
the
could you
resource.
repeat it once again? Sir, could you repeat it once again?
Yes.
Sequencing condition must be set.
Yeah, so this is basically the data dependency constant, right? So basically what it means, that the way this operation 6 and 7 schedule, that so if operation 6 start at certain time, it should finish its execution, then only 7 can start, right? So this is nothing but this. So if operation, so as I already mentioned that for operation 6, either 6.1, x61 or x62 will be 1, right? So either it will start at time step 1 or time step 2. So if it is so basically this says that this is the possible start time of operation 6. So if it is start at operation time step 1, this is 1 into x61, and if it starts at time step 2, it is 2 into x62. So the possible start time of operation 6, and this is nothing but the possible start time of operation 7. It is either in operation second time step 2 or 3. So you can understand this. So they should satisfy the execution time of 6, which is basically 1. Right? So this is basically, or in other way, it is actually satisfying the dependency constant, I'm just representing that particular requirement is like this, that execution time of 6 and 7 ensure the execution time of operation 6, right? And this is what this equation means. I think it's clear, right? And
Yes, sir.
yeah, so similarly for each age, I am going to add a constant like this, right? So I have two set of constant is done. Now the important constant is the resource constant. Since I told, so let me, so here for each type of resource I will have a constant, right? So each type of resource, each time stamp you have a constant. So if there are two, so for our example there are two type of resource, two, and our lambda was 4, so there will be 8 such constant here, right? So for each timestamp, for each type of resource, we'll have a constant, right? Because I have to make sure that for each timestamp, the resource bound is satisfied for each type of resource. Okay. So let me consider only say multiplier now, and then we'll have the similar kind of constant for ALU also. So if I take the timestamp 1, I'll see what are the operation is possible to start at timestamp 1. It is either, so 1, this operation 1, 2, 6 or 8. So there are 4 such multiplication operations. So they can start at timestamp 1, right? So this is the x11 is basically means that this is the operation 1 if starts an timestamp 1. So this will be 1 if operation 1 is going to start at timestamp 1. Similarly, this is basically if operation 2 is going to start at timestamp 1. This is operation 6 if it starts at timestamp 1. And this is operation 8 if it starts at timestamp 1. So this summation of this saying that the possible operation which are actually is allowed to start at timestamp 1, right? So their summation should be less than 2. What does it mean? At most 2 of them can start at timestamp 1. So not all 4 can be start, because it will be it will be stopped by the resource constant, because I have 2 multiplier available. So only, although 4 operations are available to start, 4 multiplication operations are available to start at timestamp 1, but only 2 of them are allowed to start. Okay. So similarly for timestamp 2, I'm going to calculate the same thing. In timestamp 2, either 3, 7 or 6 and 8 also can start here if you just calculate the mobility. So the either 3, 6, 7 or 8 can start, but again only 2 of them can start here, right? This is how in timestamp 3 also I have to add a constant, timestamp 4 also I have to add a constant for multiplier, and similarly for ALU I have to also add a constant. So these are the 3 set of constant I have. And then I already told you this optimization function, which I already told you that if all 0 and the last bit is 1, which is nothing but the minimization of the sync time. Okay. And in the last class, I told also that if all of them is 1, what does it mean? So you try to minimize the value of, all start time, right? So the start time is, so basically you try to minimize the start time of all. So if all of them is 1, what does it mean? You try to minimize this expression. Say, so let me just write here. So T1 plus T2
Sir,
plus,
excuse me, sir.
yes.
Sir, could you explain what is exactly C matrix represent? Like, what is
Yeah,
it?
I'll explain once, right? So yeah, so if you have any question, you just stop it, because I cannot see your expression, right? It's a very dumb interface, right? I can't see your expression, whether you understand or not. So feel free to stop me. I can repeat. I'm repeating the whole thing again because I have explained the same thing in the last class also. But I feel it is a little bit mathematical thing, and we need kind of repeated explanation, right? So what I'm saying that this minimization is basically C is a vector of constant, right? So of size n. Okay, in this particular formulation, since there are so t is a vector of start time. So since we assume that there are n such node, so t1 is basically telling that start time of operation 1, t2 is start time of operation 2, and tn is the start time of operation n. And c is a vector of some constant. Okay, it's a vector of size n of constant. And what is this? Is basically your transpose. Ct is the transpose of c. So it's basically is n. So ct is nothing but n cross 1, right? And then t is what? But this is a matrix. You can assume that this is a matrix n cross 1, and t is nothing but 1 cross n, right? So now we can multiply. This is a matrix multiplication, nothing else. right? So it's basically n cross 1. So CT is the transpose of C is nothing but it's basically n cross 1. So it's a basically a column vector, right? It because CT become a column vector 0 0 0 0 1, and matrix, this is a variable which I don't know. So it is basically 1 cross n. So it's a matrix multiplication, nothing else. But if you just do a one column with one matrix, you'll get 1. So the result will be 1 cross. Sorry, this is uh, yeah. So this is yeah. So now if you assume, the result can be n cross n. But what I'm trying to say is that if all of them are 0, eventually you'll get, if you multiply these two expression, eventually you'll get a single variable minimization of Tn. Rest of the things will be 0, because whatever you multiply, it will become 0. So if you just consider this vector, so this will result in minimization of Tn, right? So mean Tn, that's all. So you try to find out the value of this xij such that they satisfy all these constraint, and you get this Tn value as minimum. Understood?
So basically the T vector T array will have this thing, that is like start time of each thing. So in this case it will be 1 2 3 4 5. Is it like that?
Yeah. So say suppose operation 1 start at 1, operation 2 also start at 1. So suppose this is starting at 1. So this is not given, that is already obtained, right? So Tn is not known to us. So I try to find out the value of T1, T2, T3, Tn such a way that this particular expression become minimum. Okay. So it is not known to me, because that is what I'm trying to figuring out, right? The scheduling is something which actually identify the value of T1 to Tn, right? So I want to find out the value of T1 to Tn such a way that this multiplication, this expression, this result of this expression value is minimum, right? So then now my scheduler or the ILP solver will try to figure out the value of this this T1 to Tn such a way this expression value is minimum. Okay.
Hello, sir. Sir, can you repeat on like how we all get the value of lambda?
Yeah, so this something the question in the last class Rakesh also asked. So basically the question here, I'm going to explain that. Just hold for a minute, okay? What is the lambda and how lambda is fixed here? Because all the equations are basically depend on lambda here, right? I'll explain that in a minute. But did you understand this formulation, everybody? If anybody has a question, you can just raise your voice. I hope you understand this. So,
Sir, excuse me,
yeah,
sir. So,
yeah.
what will define the values of this C vector? Basically, I mean, is it that for simplicity we are taking it as 0, 0, 0 and
No,
1?
no, it is basically based on your objective function. Okay, so it's basically your decision. It's a constant vector. It has to be provided to the solver. So based on your objective function, suppose if you want to optimize the lambda or the latency, then you make sure it is 0, 0, 1. I'm going to explain the same thing again. Now, if you consider as all of them is 1, right? So then what is the expression? It is basically minimization of this expression T1 plus T2 plus T3 plus Tn. So what does it mean? I try to find out the value. So my whole purpose is to find out the value of T1 to Tn, right? So I am going to find out those values such a way that this whole expression value is minimum among all possible values. Right? So this T1 to Tn has many possible values. I am going to assign the value of T1 to Tn such a way that the overall summation of this T1 plus T1 plus T2 plus T3 to Tn will be minimum, right? So when I'm going to consider the value of C1 is basically all 1. Did you understand? And now what does
Yes,
it
sir.
mean? Because
Okay.
I do not have any T1, T2 and T3, right? Because T1 is represented by what? I have already explained, right? So what is Tn? T1. T1 is nothing but this, right? So this is the T1. Basically this is what my T1, right? So this 1 into x11, because there is no T1 in my whole formulation, right? So T1 is represented by is 1 into x11 plus 2 into x12 plus 3 into x13 plus 4 into x14, right? So this is nothing but my T1, right? Similarly I have T2. Okay. So so if I just tell this, what the solver will try to do, because this is my T1, right? T1, because if you consider this graph, for this graph T1 the mobility was only one value, right? So if you just remember here, I just told you this is my x11 is true, right? So but because this operation 1 can only schedule in timestamp, so x12 is 0, x13 is 0, x14 is also 0. So the start time of T1 is basically, I'll just explain this way, right? So T1 is basically x11. What is T2? T2 is similar, it can only schedule here, right? So that means this is x21, right? So this is T2 is nothing but x21. So what about T6? I'll just explain. So what is T6? It can schedule in timestamp 1, so x61, or basically 2 into x62. So this is the possible value of, this is the T6. I can represent T6 just like this. So what about T10? So T10 is nothing but, yeah, T10 is basically 1 into x10 1 plus 2 into x10 2 plus 3 into x10 3, because operation 10 can execute either in timestamp 1, 2 or 3, right? So this is the value of T1. So now if I just say that I want to minimize, so if I put the value of C1 is this all 1, so then my optimization goal I want, so this is the possible value of T1, this is T2, this is T3, sorry, this is T2, this is not T2, this is basically T6, right? Sorry, this is, sorry, I'm sorry. So this is basically T6, right? And this is T7, this is T8, this is this is T8, this is T9 till this point, right? So this is the T9. So I'm just putting this all the value of T1, T2, T3. I'm not putting the value of P1, P2 because their mobility is fixed. I'm not, because whether you put them in an expression or not, it doesn't matter, right? So they are basically fixed value. So what I'm doing, so if I just put this value C1, C is all 1, it's nothing but I try to solve this equation. I want to find a value of this particular expression minimum, right? The value of this expression should be minimum. The way I'm going to put the value of x1, this all this Boolean variable. Is it understandable now?
So if it is like finding the minimum of T1 plus T2, like T1 plus T2 till Tn, then it should be like T into C, right? Like why we are considering C transpose into T.
Can you repeat your question again?
So basically we are finding minimum of one expression, just
Yes.
a single expression. So,
Yes.
but C transpose T will give me n cross n. Instead, if we have T into C, like T into C, we will be having just a single expression of which we are
Okay,
finding
I
minimum.
think so maybe this dimension probably I just stated wrongly. So this is basically sorry. So this in my, I think the way I'm trying to say is basically 1 means number of row, right? So it is basically n cross 1 or 1 cross n. C is 1 cross n, I guess. So this is
Okay, C is a row matrix. Like C transpose is a row matrix. C is a column matrix.
so basically the dimension you can understand, but the overall if you just multiply two such vector, you will get one vector only. Either it will be one column or on one row, it doesn't matter. So that size something n cross 1 and 1 cross, so you can actually, I think this is 1 cross n into n cross n, or but finally you'll get a vector, right? So basically if you just try to understand the way I just explained here, right? So that whenever you have this 001, finally it is nothing but only Tn, right? And if it is all 1, is nothing but identifying the this value, minimization of this value, right? So this is what I'm going to do, and now you can put any other value, right? So this C can be a vector of n, I mean size n of any size, it can be any vector. So then it actually either it is a meaningless or it actually solve a purpose, right? But usually for a time MLRC problem, this is 0001, right? Because I want to minimize the latency. So is it clear to everyone?
So
Yes.
So why we are considering C as 111? Like our final motive is to find C at 0, 0, comma 1, like only at 1 at the last, right? But why we are considering in the second case we have written all
I
ones?
am just explaining that. So if you can utilize the same ILP formulation to solve a different problem as well, because so if in our problem that ML minimize latency under resource constraint, for that C will be this. But if I consider them, it is not MLRC problem, but you try to identify the earliest start time, or you try to identify the start time such that or the summation of their start time is minimum. Right? So that is then your objective function may be different, right?
Okay, sir. Okay, sir.
Yeah. So it's not that. So for our problem, yeah, you are right that the C will be all 0, 0, 1. But you can actually use the same constraint, this start time, unique start time, dependency, and resource constraint, and you can solve another problem by considering a different, just considering the different value of C. That will give you the different solution. I'm going to solve the MRLC problem immediately after this, which also I will take the same constraint again. Okay. So now the question, yeah,
So
please.
like when we are talking about these operations x6 and x8, like you are saying the mobility is only 1 comma 2, but you are getting those mobilities from the ASAP and ALAP algorithms, right, where you are not considering the resource constraints. So
Yeah. So
how can those values be correct here?
yeah, it's a very good question. So the point here is that, uh, and you have a similar question that about the lambda upper limit, right? So what we are explaining here that I am considering lambda equal to 4, right? So all the explanation here considering the lambda is equal to 4. Okay. So lambda equal to 4, and I know that for this particular example, this is the minimum value which I obtained from this from ASAP and ALAP solution. Okay. Now the previous your friend asked the question, how do I know the value of lambda? It's a very good question, and the question here is that, and the answer to this question is that if I say assume this particular graph, I took lambda, right? And I know by ASAP that lambda equal to 4 is the minimum value. I cannot have a schedule with unbounded resource also, a schedule which less than lambda equal to 3 or 2, right? I need at least 4, lambda equal to 4 to schedule this behavior. So that ASAP gives me. Now the question here is that, say I have explained everything with lambda equal to 4, and you have and say suppose I got a solution by ILP. What does it mean? That is the optimal solution, right? So the way you should look into this problem is that because lambda is not known to me, I have only the resource bound is given to me. So I will run ASAP into this graph. I'll get the lower bound of latency. I try to solve the problem for the lower bound, right? Lambda equal to 4. And if my ILP give a solution, it is guaranteed that the solution that I obtain is the optimal, because there is no solution that exists less than 4. So with that resource, this is the optimal solution. Okay. Now suppose the resource constraint is given such a way that your ILP says that no solution exists for this, right? So then what will happen? It will basically say there is no solution exists. Then you have to take lambda equal to 5. So with lambda equal to 5, your mobility will again change. You're able, if you remember the ALAP algorithm, so ALAP algorithm we give a value lambda also. So if I give the value of lambda equal to 5, ALAP solve the you'll find the latest possible timestamp considering the limit is 5, and then all your this mobility will change. So I mean this can be a good homework for you, that you consider this lambda equal to 5, and you consider the this mobility, and their mobility value will for this, if the lambda equal to 5, the mobility of when this operation 1 become in either here or here, because this operation can go to timestamp 5. So there is a buffer in this critical path as well, right? So
So,
yes,
but that one like only works for ALAP, right? In the ALAP, we give lambda, so based on that we get the late values. But in
yes.
ASAP, we can't give the lambda. So how can we get the ASAP timings of a lambda equal to 5?
So that is what my question. So ASAP independent of lambda, right? ASAP return lambda. It does not take lambda as input, so it is always give you the earliest start time, right? So and it does not change with value of lambda, right? ASAP is just, when for a given graph the solution is unique, you cannot have a multiple solution. ASAP always give you unique solution. It doesn't matter what is the lambda, because it return you the lambda, right? On the other hand, so I'll go to that slide. I think that will clear your doubt. Uh, yeah.
No, sir, I
So just a
understood that.
second.
My main
Yeah.
doubt is that will it be okay? Like in one graph, the lambda is 4, and another graph, the lambda is 5. Can we use those two graphs to find the mobility? That is the main doubt.
No, so that is
Because,
my question. No, so ASAP, you see, ASAP does not take lambda as input, right? It
yeah,
takes a graph and it will return you the lambda. Okay, so it is basically unique for a graph, right? Given a graph, it will always, every time you run, it will give you the same value for all T1. The T1 T2 will be same for every node. Okay, but for ALAP, I am giving the input lambda bar also, right? So if you run ALAP with lambda equal to 4, you will get a one set of time start time of the variables. If you give lambda equal to 10, you will get another set of start time. So that will vary, because ALAP, based on this limit given, it will try to find out the latest possible start time of the variable. And now, for a given lambda 4, the mobility that will be calculated will be different when you actually consider lambda equal to 5, because ALAP solution is completely different, right? So, but the approach that we should follow here in this resource constant formulation that I just discussing here, that we usually will take the minimum possible value what the ASAP solution gives us, the minimum possible latency, and then I'll run ALAP with that to identify the mobility of the operation. But that particular minimum timestamp resource availability may not allow you to do that. For example, suppose here, when now we are familiar with this graph, so here you can see that this operation can move here, this operation can move here, but at least I need two multipliers, right? These two operation cannot move at any, so to schedule everything in lambda equal to 4. So now if say the one multiplier is given, so whatever the formulation you will do here, it will say that there is no solution exists with this, because there are at least need two multipliers. But then say then so there is no schedule available to schedule this behavior with one multiplier in 4 times time, right? So then this is not possible. Then I have to take 5, a lambda equal to 5. With 5, I am going to calculate the ALAP again. I'll run the ALAP algorithm again. I'll get a different set of latest possible value, and for that I'll get a different set of mobility. My all constant will change now. This constant will change now, because all this timestamp everything got changed. So all these three set of constant will be changed now. With this, I get a solution. So if I get a solution with lambda equal to 4, that is the optimal solution, even with the resource constant. But if there is no solution exists for such minimum lambda, I will increase the lambda. I'll get the different set of mobility, I'll get a different set of constant, and then I'll get a different solution, and that is not optimal. Okay, but that may be the only feasible solution with such resource available. Understood?
yes, sir.
Okay. Okay, but these are very good questions. These are the things you should understand. Otherwise, I mean, it is the whole formulation will be clear, right? And actually, you can actually make a try that you can actually. There are many ILP solver available online, free. You just solve this constant, take this graph, you try to solve this problem. You give graph whether you are getting solution or not. So that will solve your, and it will give you a lot of insight how the ILP works and all, right? It may be a good idea to try few such things. Okay.
Sir, sir,
Yeah.
just for clarification, what you
Yeah.
said right now was that is if minimum lambda doesn't work, increase the lambda, again do ALAP, then again find the results, like do ILP, like for finding the solution for that lambda. That's what you said.
Yes.
Okay.
Yes. Okay. So this is what I just talked about, this minimization of latency under resource constraint. And so if you take all 0 and this 1, and then you solve this problem, and you will get this solution. You can try that, right? So you can see here when it's satisfying the 2 multiplier requirement, right? So this is satisfying, and I am able to schedule in 4 times, right? So that is the solution we obtained from here. Okay. So now I'm going to talk about just the ILP formulation for the dual problem, right? What is MRLC? That means my lambda is given now. I cannot change that now. Okay. So now all the confusion is gone. So I want to get a schedule with time step 4 within 4 timestamp which utilize minimum number of resources, right? So that is what is this formulation. It is just the dual problem of the previous. Earlier one was the MLRC, this is MRLC, right? What does it mean? Minimization of resource. I want to identify the minimum resource requirement given a time constant is given or the latency constant is given. Okay. So in this case, what is the obviously whatever the solution you try to give, I'm going to I'm going to take the same variable again xil, the same boolean variable. Obviously, when you take that boolean variable, it must satisfy the unique start time dependency constant, because that you cannot have any solution which does not have a unique start time or a and it's actually violate the dependency constant, right? So for so even in this case, what is not known, that AK, that resource bound is not known to me. I want to find that value, right? This is not given, but lambda is given. In the previous solution, although I assume for a particular ILP formulation lambda is given, but lambda is actually I assume a value of lambda, but that is not given, and I already explained how the heuristic should work. That you consider first the minimum, the value of lambda. If there is no solution exists for the minimum lambda, you increase by 1 and again run the ILP, right? So that is what I just summarized in my previous slide. But in this particular formulation, my lambda is fixed. I cannot change it. But this AK is not given to me, right? This AK, the resource constant, is not given to me. Okay. And I want to find the value of AK actually. So that is my objective. And so basically here, because the latency bound is given, I have one more constant to be added, right? So the constant is basically the start time of the last node or the sync node NL should satisfy this lambda plus 1. So whatever the solution I'm going to find, that satisfy the latency bound. Again, my ij is not known to me. That is what I'm going to find out. But whatever the value I'm going to find out, this must satisfy the latency constant, right? So I have constant like, so I have unique start time, I have data dependency constant, and I am going to use the same resource bound. Only thing is that here instead of 2 I am going to write a1 and so on, right? A1, A2 and A3 for so because that A is not known to me also, right? And in fourth, so in addition to this 3 constant, I have the fourth constant, which is basically the latency bound. Okay, is it clear to everyone?
Sir, we should find the minimum of that this thing, right? In the previous
I'll come
page.
to that point. So I have not defined the optimization objective yet, right? I'm just defining the constant, right?
Okay.
What I'm arguing that whatever the solution I have, it should have unique start time, dependency constant should be satisfied, and resource bound should be also satisfied. Only thing is there here, the resource bound is not fixed, it is basically variable, A1, A2 and so on, right? And fourth constant is whatever the solution I'm going to get, that must satisfy the latency constant. So the sync node time start time must be less than lambda plus 1. Okay. So till this point is clear, right? Now what would be my objective function, right? Or the minimization function. So here my minimization function is CTA, because I want to find out the value of A. So A is the vector of the resource bound that I'm going to obtain, right? So this A is a now vector of A1, just yeah, A2 to AN resource, right? So this is not n for each operation now. This is the now the variable A1 to N resource which I am going to identify by my ILP, and C is what? C is now a fixed constant. Again, the constant vector, which is the cost of individual operation, right? So this is again a constant vector, which is basically the cost of operation 1. So if say 1 and then say 2, say 0, say 10, say 1, then so on, something like this, it means the cost of doing operation 1 is 1. I mean, operation 1 is 1. cost of performing operation 2 is 2, cost of performing operation 3 is 10, and so on, right? So it's a fixed value, and it basically cost can be a measure of area, as I mentioned, because I want to have a resource constant in the area constant. So it basically the value, the relative value of the area that is needed to examine of that particular multiplier or adder in the actual hardware, right? So what I'm trying to do here, I try to multiply this cost of those operator with the value that I'm going to obtain, and I want to minimize that value. So what does it mean? I'm going to so say suppose this is basically then C1 into A1 plus C2 into A2 and so on, right? Then Cn resource into An resource, right? So I want to minimize this expression. So I want, because I know, so that means if say multiplier cost is 10, so if I use one more multiplier, that means 10 unit this use more cost, but I can add, if I add one more adder, my cost will be increased by 1 unit, right? So you understand that now I have the same set of constant, right? I have the same set of constant just like previous. Only thing is that yeah, this is unknown. This value is unknown plus the latency bound, and my objective function is now completely different because I want to minimize. I want to identify this value of A1 to N resource, and so such that the overall cost of this area is minimum, right? And this cost is basically C is thus the area value, relative area value of this those particular operator. Now if we solve this, I'm going to get a solution which will give you the maximum minimum value of A1 to N resource. That will give you the resource bound. So I'm making sure that I'm getting a solution which satisfy my latency bound, and it's giving me the minimum resource requirement to schedule all those operations within that resource bound or within that latency bound. Okay, I hope it is clear. So just to clarify, I mean that initially it was in this here it will be A1. So I will have a constant for each timestamp, right? So similarly, if this is for A2. So if I just refine this third constant, my third constant will be defined like this resource constant. Instead of 2 or something, I can have only the value of A1 and A2. And if I assume the cost of multiplier is 5 and add is this, so my objective function is basically 5 into A1 plus 1 into A2. I want to minimize the value of this. I want to find out the number of resource A1 and A2 such that the total value of this particular expression is minimum, right? We satisfy all this 4 set of constant. Okay. So with this I'll conclude, and then I'll go to more discussion on ILP in the next class for a simplistic solution. Any question? I can clarify again.